Hello everyone, and welcome back to Networks class. Last time in class, at the beginning of class, we went over homework 3.1. And towards the end of class, we saw an example of running Ford-Fulkerson algorithm on a rather complicated graph with capacities. And we saw that the Ford-Fulkerson algorithm is kind of like a little special purpose LP solver. So at the end of the algorithm, if you have the original graph and the final residual, you can pull out all the information you need. For example, what the trucking plan is, how much flow we're moving from S to T, what the minimum cut is, etc. And the plan for today is to just wrap up a few things about Ford-Fulkerson. So in particular, we never really got to talk about the runtime of Ford-Fulkerson, so we're going to do that today. And then we're going to look at a couple of applications of max flow. So these are problems that you can solve with max flow that it's not necessarily immediately obvious how to solve them using max flow. So let's begin by talking about runtimes of Ford-Fulkerson. And to do that, let's take a look at a particular example. So here's an example. So we have S, 1, 0, and T. And let's say this edge has a capacity of 1,000,000. And this edge has a capacity of 1,000,000. Same with this one. And this one. And this edge has a capacity of 1. So Ford-Fulkerson says find any path from S to T. So suppose that the path we find is S0, 1T. So in this path S0, 1T, we can only move 1 unit of flow. So let's write down what the residual graph would look like after we add that unit of flow. So here I'd have a capacity of 999,999 and 1 in the reverse direction. This edge would get reversed to 1. Here we'd have 999,999 and 1 in the reverse direction. And then these two edges would be the edges we didn't touch. So in the next iteration, we'd ask Ford-Fulkerson, or Ford-Fulkerson would find a path from S to T here. And let's say that the path it found is S10T. So on this path, we can add 1 unit of flow. And so you can see what's going to happen here, that we basically need to do 2 million iterations to actually complete this example, because I could always find this path and then the opposite path and so forth, and I would only stop when I sort of actually find the max flow value. So this is kind of a problem because the runtime is kind of dependent on these capacity numbers. So let's make that a little bit more explicit. So in each iteration, Ford-Fulkerson increases the flow by at most 1. So we could have as many iterations as the max flow value. Because in each iteration, we increase the flow by 1 in the worst case. So let's just figure out the max flow value. If there's an upper bound we can give on that max flow value regardless of what the graph is. So consider just the node S. It has coming out of it n-1 edges. And each of these edges has a capacity on it. And let's say that Umax is the maximum capacity over all edges in the graph. So if each of these edges potentially has a capacity of Umax, the total flow coming out of S is about n-1 times Umax. So the maximum flow An upper bound on that would be something like n times u max. And you can think of this just kind of as a independent upper bound, the same way that n times c max was an upper bound on the shortest path length. So n times u max is the biggest that the max flow can get. And so the number of iterations could be as big as n times u max. But what's the runtime per iteration? So what has to happen in each iteration? We have to find a path from S to T. And finding a path from S to T, we would do using one of our search algorithms like BFS or DFS. And so that takes O of n plus m time. And then we also have to update the residual graph. And the updating of the residual only happens on the edges that are on the path. And there's at most n edges on the path that we find. And updating the residual for each one of those edges just takes a constant time. So updating the residual takes O of n time total. So that means that each iteration takes O of n plus m time total. So the overall running time of Ford-Fulkerson is just the number of iterations times the time per iteration, which is just O of n times u max. And then the time per iteration is n plus m, but let's just simplify that to O of m by just assuming that we have more edges than nodes. So I'm going to multiply this by m. And typically people write this as something like nm u max. And this is kind of an unsatisfying runtime. And the reason it's unsatisfying is really because of the u max. The n times m part here, that doesn't worry us too much. I mean, even though n times m is significantly slower than the n plus m algorithms and the n log n types of things that we saw for Dijkstra's, what's really the problem here is this u max. So in this example, we have a very small number of edges and a very small number of nodes, but it still takes forever because these capacities are big. And in particular, I want to point out that this u max here is actually exponential in the size of the input. So it takes us 6 digits to specify this number, 1 million. So, 6 or 7 digits. But it's going to take us 1 million iterations to actually solve this problem. So the problem here is that the problem specification is very small, but it takes forever to actually solve. So we're not happy about this, but it actually turns out that practically Ford-Fulkerson is not that bad. So the reason for this are a few things. So first, it turns out that if you use BFS to find paths from S to T, then you can show the runtime is slightly better, so we can get rid of the Umax. It's just O of n times m squared. So it's still not great. N times m squared is significantly slower than runtimes for Dijkstra's. But let's compare it with how long it takes. So how long does it take to solve max flow using a general purpose LP solver? Well, a general purpose LP solver is O of big times small squared. So we just have to figure out what big and small are for the max flow problem. So how many variables does the max flow problem have? Well, we had the yij variables and we had a v variable. And those are the only two types of variables in the max flow linear program. So there's one y variable for each of the edges, so that's m. And there's just one v variable, so just m plus 1. So what about the number of constraints? How many constraints does the max flow problem have? Well, we have all the network flow constraints. So that's the number of trucks coming into a node has to equal the number of trucks going out. So there's n of them, one for each node. So that's what we've been calling the network flow constraints. But those aren't the only constraints that we have. We also have these capacity constraints that basically say the number of trucks on each edge has to be less than the capacity of the edge. So we have one such constraint for every edge. So these are the capacity constraints. So comparing these two things, big is the number of constraints and small is the number of variables. So the runtime is O of n plus m times m squared. And that's because the number of variables here, really, you could just think about it as m. That one doesn't really make much of a difference. So it's n plus m times m squared. So comparing these two, the general purpose LP solver to what we get with Ford-Fulkerson. Ford-Fulkerson is already beating the general purpose LP solver. So in particular, it's beating it because it doesn't have this m cubed term over there. But still, there's tons of other algorithms out there for max flow. So there are other algorithms that work on an entirely different basis than Ford-Fulkerson. So let me just tell you about a few of them. One of the algorithms can give you a running time of O of m squared times log of Umax. So here we substituted that Umax for log of Umax. And so going back to this bad example, the runtime here would be something like the order of 6 because the log of a million is about 6. So we're getting back to that area where we're not exponential in the size of the input. You're just still have a reasonable polynomial of the size of the input. So the way that this algorithm works is it essentially just filters out small edges. So it'll begin with a threshold. So imagine that here is Umax. So that's the biggest threshold that's the biggest capacity that any edge can have. What this algorithm will do is sort of set a threshold that's kind of in the middle and only consider edges that are bigger than the threshold. So it'll try to find paths from S to T, kind of eliminating these small edges that might be a distraction. So in terms of this problem, when we set the threshold to be half of the maximum capacity, it would be about 500,000, we would immediately eliminate this edge. And so the paths that we find from S to T would be pushing on the order of 1,000,000 units of flow every time that we actually find a path from S to T. But eventually, we're trying to find paths in this filtered graph where we've dropped the small capacity edges. Eventually, we're not going to be able to find any more paths. And then what the algorithm does is it just decreases the threshold. So it halves it to half of what its original value was, and then continues to try to find paths from S to T until it can't anymore, and then halves that and halves that. And so that's where the log of Umax comes from, because that's the number of times that we have to decrease this threshold before it reaches 1, at which point we know that we're considering all of the edges in the graph. And the m squared here comes from the fact that each iteration of this algorithm takes about m squared time. So there's an algorithm that gives you that running time. There's lots of other algorithms. And we're not going to study these other algorithms in class. They're in the Ahuja, Magnanti, and Orland book if you're curious and you want to take a look. But let me just write down some of their running times. So the kinds of running times that they give you is O of n cubed There's a different one that gives you O of n squared square root m. Another one would give you O of nm plus n squared log u, and so forth. So these algorithms here work on a very different kinds of ideas than Ford-Fulkerson. So Ford-Fulkerson, every time that it finds a path from S to T and increases the number of trucks moving from S to T, it's kind of maintaining a feasible shipping plan. So at any point, we could just stop the algorithm and ask, what's your shipping plan right now? And would give a shipping plan that makes sense. But these other algorithms that work a lot faster, they basically work by creating infeasible shipping plans. So at the beginning, they'll start just shipping out a tremendous number of trucks out of S, completely breaking down the various capacities that we have on the edges. And then later, the algorithm kind of backs down to come down to something that's feasible. And so these algorithms are kind of more complicated than the things we want to get into in class, but they're out there and you can look them up if you need to. And they're in the Huja-Magnanti and Orlin book. So just one quick question here. If you were given these two algorithms, one that runs in n cubed time and one in n squared square root m, the one that you would prefer really is this one because m is always less than or equal to n squared. So, and by the way, all of these are much better than the nm squared that we're getting out of Ford-Fulkerson. So that's the basic idea behind the various algorithms that we can use to solve maximum flow. And so if you really wanted to solve a big max flow problem, you would use one of these algorithms that is implemented in some kind of a computer library. So let's move on to the second part of class today, which is some applications of max flow. So the first application that we'll look at is an application called producer-consumer. So the idea here is that we are given a graph of ports. So each port is either a net producer of grain or a net consumer, or just a transshipment point. And what I mean by transshipment point is that it neither produces nor consumes. But a producer could also be a transshipment point, and a consumer could also be a transshipment point. But these ports that are only transshipment points, they neither produce nor consume. And also, each of the shipping lanes between ports has some capacity that limits how much material we can put on that particular shipping lane. And the basic question of our problem is the following: can we satisfy all the grain demands given the supplies? So can we somehow move this grain from the producers to the consumers? So mathematically, this problem is just saying the following. Just find a feasible solution to the following system of equations. So for each node, We're going to have the number of ships coming into the node minus the number of ships going out of the node. And that's going to be equal to this value that basically tells us whether the port is a producer, consumer, or a transshipment point. So this is going to be negative for a producer, positive for a consumer, and 0 otherwise. And besides satisfying these network flow equations on each node, we also have to make sure that the yij's are less than the uij's. So that's satisfying the shipping capacities on each arc. So let's think about how we might go about solving a problem like this. So let's here just draw an example graph. So here's the graph. And maybe let's say that the producers are over on this side. And the consumers are over on the other side. And let's say that this producer produces 2, this producer produces 10, this one produces 5. This consumer here consumes 3, this one 8, and this one 4, something like that. And what we want to see is whether we can actually move all the supplies to the demands. So you can already see that we can do a quick check by just summing up all the supplies and summing up all the demands to make sure that they're equal or that we have enough supply to meet the demand. But suppose that they happen to be equal. So then how could we possibly use max flow to figure out a shipping plan? Well, to do that, we have to make 2 units appear in this top node. So we need 2 units of material to just appear out of nowhere in this top node. So the way to do that is we're going to introduce a fake start node S. And this 2 units of supply is actually going to become a capacity on that arc. So what that does is it basically says that at most 2 units of material can show up at this node. So similarly, this 10 would get transformed to a capacity right there. And the 5 would get transformed to a capacity right there. So in a similar way, we need to have 3 units of goods kind of disappear at this node. So the way that we're going to do that is we're going to add a capacity of 3 that goes to a fake node T. So similar for the other 2, so this 8 is going to become a capacity here, and this 4 is going to become a capacity on the bottom arc. So 8 and 4. Okay, so now we've transformed the producer-consumer problem into a problem with max flows. And the question is, what's going to happen when we find the max flow? So suppose we find the max flow, and let's say that this edge right here is not saturated. So we end up not moving 4 trucks across this edge. What that means is that we didn't satisfy the demand for this consumer. We weren't able to actually get the 4 trucks that, or the 4 units of goods that he wanted. Similarly, if one of these edges isn't saturated, for example this one, if we end up moving 4 trucks here instead of 5, what that means is that we're not using all of the supply of that particular producer. And so suppose that what happens is that not necessarily all of these are saturated, not necessarily all of these are saturated, and the minimum cut in this network happens to be somewhere through here. So what that would mean is that there's in fact not enough transportation to support moving this cargo from the producers to the consumers. So it's possible that the supply equals the demand, so we can actually just clear everything, but we're not able to do it because we actually can't do the shipping. And so that's what a minimum cut in the middle of the network here would mean. So similarly, if the minimum cut were right here, if it just involved all of the edges that go to T, what that means is that the most constraining part of the network here is the demand part. So it means that the demand is actually too low. So we have plenty of supply, plenty of transportation, but what's stopping us from moving more goods is that the fact that our demand is low. And so those are just some interpretations of the max flow problem in terms of producer-consumer. And of course, if somebody actually came along and asked us what is the shipping plan to actually move the goods from producers to consumers, if everything worked out fine, what you would do is you just tell them just these Yij variables on each of these edges, because that tells you how many ships you should move from one node to another. And those Yij variables are feasible in this system of equations here because these right-hand sides allow us to be slightly imbalanced. So these equations don't involve the fake node S and the fake node T that we added. But these right-hand sides allow us to have an imbalance of 2 units at this producer. And so that's why if you look at the y's that come out of here, if we sum them all up, they're going to have 2 more things leaving than entering in the original problem. So that's the basic idea. So let's write this out a little bit. So what we did was we add fake nodes S and T. We add edges from S to every producer with capacity, whatever the supply of that producer is. And we're going to add edges from every consumer to T with capacity, whatever the demand of that consumer is. So that's the basic idea of the producer-consumer problem. So let's look at our next application for max flows. So in this application, our goal is to find a feasible flow where we have some lower bounds. So let me explain what I mean here. So mathematically, we want a feasible solution to the following system of equations. So we want everything that comes into a node to go out of the node. And for each edge, we have an upper bound as before, but now we have some kind of lower bound. So in terms of an example, here's a small example to illustrate this. So suppose that we just have this graph with 3 vertices. So let's say the upper bound here is 5 and the lower bound is 0. The upper bound here is 3 and the lower bound is 2. And the upper bound here is 7 and the lower bound is 0. So if somebody asks us to find a feasible flow in this network, we know we have to put 2 trucks on this edge because the lower bound is 2 and the number of trucks always has to be bigger than this lower bound. But if I put 2 trucks on this edge, whatever comes into a node has to come out of a node, which means I have to put 2 trucks on this edge, which then again will mean that I have to put 2 trucks on this edge. And so a lower bound in one place in the graph is going to cause flow to happen in other places in the graph. And this flow has to kind of reconcile itself so that it makes some kind of cycle here, so that the trucks are just moving in a circle to satisfy the lower bounds. So let's see how we might go about solving this. So to solve this, you can think about solving this in a couple of different ways. So imagine that I have here a node A and B, and they have an edge between them, and it has some upper bound and some lower bound. So the first way you think about it is you can just think about it intuitively or in pictures. So I have this lower bound, and what I'm going to do is I'm going to transform the graph. So to satisfy the lower bound, we need to move L trucks across this edge. So let's just pretend that we're moving L trucks across the edge. If we move L trucks across the edge, automatically the upper bound is going to get smaller. So the new upper bound here is going to be the old upper bound, but minus the L trucks that we're moving across the edge. But then the question is, where do we get these L trucks? So what we're going to do is we're going to kind of borrow L trucks from A, even though they don't exist there. And when we borrow these L trucks, what that's going to do is it's going to create a demand of L at A, because we borrowed them even though they don't exist there. So that's going to create this demand at A. And after we move the trucks across the edge, they end up at B. So that creates a supply of L trucks at B. So what we're going to do is we're going to transform an edge that looks like this into an edge that looks like this. So previously we didn't have supplies and demands at A and B, and now we do. And we also have a changed upper bound, but we have no lower bound. So the lower bound went away, and now it's 0. So that's the way to think of this in terms of pictures. But you can also just think about this algebraically. So this edge over here has a variable associated with it, YAB, that tells us the number of trucks that are going from A to B. And this variable is in exactly 4 constraints. So the 4 constraints that it's involved in is that we know that it has to be bigger than or equal to its lower bound. We know that it has to be less than or equal to its upper bound. And it's also involved in the network flow constraints for A and B. So we know that it's involved in constraints like that look like this. So those are the 4 constraints that this variable is involved in. And this kind of picture transformation, all it corresponds to is just a variable substitution. So let's substitute the following variable. So we're going to say that y prime ab, so that's the new variable that we're going to introduce, is equal to just yab minus lab. Or another way to think about this is that just yab, so I'm just rewriting this equation, is just yab equals y prime ab plus lab. So that's the new variable that we're going to introduce, and that's its relationship to the old variable. So let's see what happens when we substitute this new variable into the constraints for the old variable. So let's first do it with the lower bound. So we had the lower bound has to be less than or equal to yab. But we know yab is equal to y prime ab plus the lower bound. And combining these two, it just tells me that y prime ab has to be bigger than or equal to 0. So that's because we can just move this L here to the other side, and it'll cancel out with that L, and we just get the y prime bigger than or equal to 0. So that's what happened to the lower bound constraint. A similar thing is going to happen to the upper bound constraint. So if we do this substitution in here, and we move the L over on the other side, what we're going to get is that y prime ab has to be less than or equal to uab minus lab. So now you can already see where this picture starts coming from. So the lower bound for this new variable is 0. And its upper bound is this original u minus the L. So that came out of the substitution. So now let's see where these supplies and demands are coming from by doing the substitutions in here. So the variable YAB is going to show up in the second term in that equation. So when we do the substitution, it's going to look something like this. So things going into A minus, now let's do our substitution. So y prime AB plus LAB minus the rest of the stuff that's coming out of A is equal to 0. So that was just substituting our expression into this constraint right there. So now, moving the L over on the other side, we end up getting everything going into A minus everything going out of A. So now the y prime kind of got incorporated in here. And on the other side, what we're going to get is a plus L, because here we have a minus L. When we move it on the other side, we get a plus L. So that created a demand of L at node A. So that's where this demand at L at node A came from. So a similar thing is going to happen with B. So let's do that. So here's everything that comes into B. But one of the things that comes into B is our special variable here for which we're going to do the substitution. So this doesn't include node A. Plus everything that goes out of B is going to equal 0. So now when we move the L over on the other side, we get everything coming into B minus everything going out of B is equal to the minus L. And so that's what that's where this supply at B showed up in. So these are the final 4 inequalities that the y prime variable is involved in. So its lower bound is 0. Its upper bound got changed to the original u minus the L. We created a supply of L at B and a demand of L at A. So you can think of this either algebraically or just in terms of this picture and just borrowing trucks from A and moving them to B. Both are just as well. So the idea of doing this is that we took our lower bound problem and we converted it into a producer-consumer problem. So this was lower bounds, and this is now just a regular old producer-consumer. Because we got rid of all the lower bounds in favor of just these supplies and demands. And so we can solve the producer-consumer problem to find a feasible solution to this original lower bound problem. So let's do a small example of this to see how it would work. So I have a network maybe that looks like this. So here I have an upper bound of 5 and a lower bound of 0. Here an upper bound of 3 and a lower bound of 2. And here an upper bound of 7 and a lower bound of 0. So the first thing to do is to do our transformation. So when we do the transformation, there's a couple of edges here that we didn't touch. So this edge is still going to have an upper bound of 5. And its lower bound is going to be 0. So I'm just not going to write that in here. The upper bound for this edge is going to be 7. And its lower bound is 0. So I'm not going to write that here. And for this edge, the new upper bound is going to be whatever the old one was minus these the lower bound. So it's going to have an upper bound of 1. In addition to this changed upper bound, we created some supplies and demands at the neighboring nodes. So we get a supply of 2 on this node and a demand of 2 at that node. The next step is to just solve producer-consumer. So what we needed to do for that was kind of add these fake S and T nodes. So here we have our upper bound of 1, our upper bound of 5, upper bound of 7. So here we have a S node connected to a producer with a capacity of 2, a T node connected to a consumer with a capacity of 2. And if you go and solve this problem, what it's going to tell you is to put 2 units of flow kind of along this path here. So that's going to be the max flow from S to T in this particular problem. But remember that we wanted a feasible flow for this original lower bound problem. And right now what we're getting is that the flow on this arc should be 2. The flow on this arc should be 2. But the flow on this arc right now is 0. So how do we know that the flow on this arc should actually be 2? Well, the reason for this is because this 0 right here this is the y prime. And so we have to map it back to the y to actually get the feasible answer in this original problem. So you have to just do the transform back to the original variables. So when we transform back to the original variables, we get a flow of 2 here. A flow of 2 here because these 2 edges were not transformed. And we get a flow of 2 here as well because in the transformation here, to transform back, we have to add the 2 trucks that were kind of automatically moving across this arc to create this supply and demand in the first step. So that's the basic idea of solving for a feasible flow given some lower bounds. And in general, if you have some kind of big complicated graph, if I have a lower bound on one edge, it might create some very complicated circulation patterns around the graph for us to try to find a feasible flow. And this method will solve that. So by the way, just as a quick comment, suppose that I had a graph like this, where let's say the lower bound here is 5, but the upper bound here was 4. So if I have something like that, there's no way for me to find a feasible flow to this lower bound problem because I want to move 5 trucks here, but only 4 are allowed to go on this arc. And the way that you'll find that by doing this is that in this step right here, when we're trying to solve producer-consumer, what's going to happen is we're not going to be able to move all the supplies to all the demands. So we're going to get some kind of minimum cut that's on the graph, and so we know that the original problem didn't have a solution. So those are the 2 main applications of max flow that we'll discuss for today. Next time, we're going to use these as kind of sub-problem solutions to even bigger applications of max flow. So thanks a lot for listening, and I'll see you all next time.